Math 1332, Chapter 10, Probability and Counting Techniques. Section 2, the Fundamental Counting Principle, Permutations. Video 4, Evaluating Factorial Expressions. In this video, I'm not going to be setting up any word problems. We're simply going to do some arithmetic. Some of the problems we will encounter later in the section will require us to evaluate expressions involving factorials. Although you can brute force your way through these problems, and I'll explain what I mean by that in just a second, there are more elegant and efficient ways to do so. Translation. I want to show you how to do these problems faster and easier to minimize the chance of making a mistake. For this page, for these two, we just have a ratio of factorials. Evaluate 7 factorial over 6 factorial. Evaluate 8 factorial over 5 factorial. First, the brute force approach. The brute force approach is to evaluate each factorial individually. 7 factorial being 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you do these enough, you start memorizing them. For example, this one is, I used to know this. This is embarrassing. I'm going to look at it and kick myself. 5,040. Good grief. I knew that once upon a time. And then 6 factorial, you would just do 6 times 5 times 4 times 3 times 2 times 1. That one is 720. And so you could set up 5,040 divided by 720. And then at the end, you would get just 7. And you're thinking, well, that wasn't so bad. Well, wait till you see what I have in store later in this video. But there's a much more elegant and efficient way. In fact, it's so elegant and efficient that if you think about it, you could probably just write down the answer to this problem. Not all ratios of factorials, but on this one, if you take the more elegant and efficient approach, you'll get the answer before the other person even gets out their calculator. What do I mean by that? Or remember in the previous video when I said it's more important that you know what a factorial means than what it equals? Case in point, if I were to roll out these factorials, if I were to unravel them, write what they mean, 7 times 6 times 5 times 4 times 3 times 2 times 1 on top, and then the bottom, of course, the same thing except without the 7. You might be tempted to do something that would not only be right, but a very good idea. You might be tempted to cancel some things. Can you cancel here? The answer is yes, but the better answer is if you're questioning if you can cancel something in a fraction, the rule for canceling in a fraction is you must be a part of a multiplication problem and you must match one on each side. Well, everything here is part of a multiplication problem, and there's plenty that match and cancel. Now, technically speaking, when you completely annihilate one side of a fraction, like I did on the bottom, there's still a 1 left. You get 7 over 1. But if you know that there's a 1, then it's 7 over 1, which is just 7. End of story. Do I expect you to be able to look at a similar problem and do the same thing? Absolutely. What's 10 factorial over 9 factorial? Well, what would cancel? Or more importantly, what would not? Everything would cancel except the 10. So yeah, there are some factorial problems that you can literally look at, think, and go, oh, I know the answer. Now, the second one may not be. But before I expand each factorial and do some canceling, I want you to see if you can picture what would cancel and, more importantly, what would be left over on the top. Can you see it? Because if you can, then you're a step ahead of the game in terms of working these out. 8 factorial, of course, starts with 8, 7, 6, 5, and I'm going to take advantage of some ellipses. I don't like that x. That's a variable x, not a times x. I'm going to take advantage of some ellipses and take it all the way down to 1. Now, why did I choose to use the ellipses after I wrote the number 5? Because in the denominator, my factorial will start with 5 and go all the way down to 1. There's no need to write all the numbers that will cancel. In fact, you can cancel them in mass. Goodbye, all you 5 factorials. And in your head, if you can see everything after 5 is going to cancel, then that just means on the top, I have to stop right before I get to 5. Now, can you do 8 times 7 times 6 in your head? I don't know. Maybe you can. Challenge yourself. It's not as impossible as it seems. Can I? Yeah, I think I can. Give me 1 second. 336. Yeah, I'm 99% sure that's correct, but just to make sure. Yeah, of course. Did I multiply them in my head? No, I used some algebra tricks and some difference of squares, but don't worry about that. The important thing is when I roll out these factorials expansions, lots cancels, but more importantly, what doesn't? In this case, it was the 8 times 7 times 6. So before I go to the next page, I'm going to challenge you to do one in your head. This one is going to be, we'll say 9 factorial over 7 factorial. Let's think about it for a second. I'm not going to work it out, but think about it. Think about when I expand on what would match and cancel, and more importantly, what would not cancel. Well, on the top would start 9, 8, and then everything 7 down would cancel, so that would leave 9 and 8. 9 times 8 is 72. Did you get it? Great. If you didn't, that's okay. You don't have to do them in your head, but I do like challenging you. Now, sometimes they get a little bit trickier. Like if you notice, these have, the first one has 2 factorials in the denominator, and you might think the bottom one isn't that bad, and honestly, it's not, but there's a reason that it's there. Let's take a look at the first one. 9 factorial over 7 factorial times 2 factorial. Well, I know what the 9 factorial will do. It will go 9 times 8 times, in fact, isn't that the one we just did? I swear that was complete coincidence. 9 times 8 times 7, and then I'm not going to write the rest after the 7. I'll just use some ellipses because I already know that the 7 factorial on the bottom will give me enough ammunition to cancel everything the tail end. In fact, let's go ahead and do that. But be careful. There is still more left in the denominator. That first factorial got multiplied times 2 factorial, but 2 factorial is just 2 times 1. So with that extra factorial on the bottom, I don't get this massive cancellation in the denominator, or rather I should say complete cancellation in the denominator, at least not yet. I always try to take out the largest factorial I can, which was 7. The smaller one still remains, but remember the rule for reducing in a fraction. Any factor, any part of a multiplication on top can reduce with any factor or any part of a multiplication on the bottom. Look at this 8, look at this 2. Because both are parts of multiplication problems, I can divide them individually. 2 goes into 8 4 times. And notice the only number left on the bottom is a 1. That's a great number to have on the bottom of a fraction because it doesn't matter. But what number survived all the canceling on the top? That 9. And that 4, which was left over when I divided the 8 by the 2. Which leaves us 9 times 4, which is 36. This factorial is equal to 36. Now, if you're thinking I can't do all that, you're wrong. You can. What you're saying is I don't want to try to do all that. So many people have this misconception that I can't do math. And you've got this incorrect perception that you can't do it. When I know that you can, it just involves knowing what to do, practicing, practicing, and practicing. So before you just say, I'm going to get out my calculator and figure out that 9 factorial is 1 million and some junk, and the 7 factorial is 5,040, 2 factorial is 2. I'm going to multiply 5,040 times 2 and divide it into that 1 million junk number up there and get 36. You do all that. And while you're making sure that you push the buttons on your calculator correctly and hoping that you do, parentheses around the denominator, we'll already have the problem finished. Now, I'm not saying you can do all factorial problems without a calculator. Like this next one, we are going to use a calculator, but not for the reason that you think. If you don't understand what a factorial means, you will not get the answer to this question. Why? Because chances are your calculator can't handle 160 factorial. Now, it might be able to. Getting out my iPhone right now, which does have a factorial button on it, but you have to rotate it to get more keys. 160 factorial, error. That usually means the number is so large your calculator can't handle it. So does that mean we can't do this problem? No, it just means we can't do it the brute force method. I've had people leave a question like this blank on a test because their calculator couldn't handle it. Sorry, my leg itched. When all they should have done was say, well, I know how the 160 factorial starts. 160 times 159 times 158. Notice I'm using the dot for multiplication, which I actually prefer. Times, oh, wait a minute, the bottom starts with 158. I don't have to expand it at all because I know that everything after the 158 is going to wipe out, which leaves me a smaller problem, but one that I'm pretty sure my calculator can handle. 160 times 159, which is equal to 160 times 159, 25,540. I'm sorry, 25,440. So knowing what the factorial does didn't get you the answer, but it got you a problem that was easier and in some case possible in your calculator as opposed to the original one. Expect this on your homework. Don't be surprised if you see something like that on your test. One that forces you to understand factorials without relying on your calculator. All right, let's take it. Whoa, Nelly, what is up with this? Trust me, these problems were not selected at random. In fact, the first one is making its third appearance in this series. You just don't know it yet. Evaluate the following: 8 factorial over 2 factorial, 3 factorial, 1 factorial, 1 factorial, 1 factorial. This is really just more of the same. None of the factorials on the bottom are really large, so there's no advantage to not unraveling the entire numerator. 8, 7, 6, 5, 4, 3, 2, and 1. And now we have 5 different factorials on the bottom to unravel, but they're all really small. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And we didn't talk about 1 factorial, but it starts and ends at 1. So each 1 factorial is just a single 1. Now, the nice thing about 1s when it comes to multiplying is they don't really matter. So if they sit there, that's okay. The biggest chunk I can cancel at once is 3 times 2 times 1. And look on the bottom. What's the only factor that's not a 1? This 2. Is there anybody on top I can reduce it by? Sure, the 8, the 6, the 4. Let's just reduce the 8. 2 goes into 8 4 times. And notice that the only numbers left on the bottom are a bunch of 1s, which means the bottom of this fraction is equal to 1, which means it's not a fraction anymore. Who survived on the top? That's the problem with these, is that you've got this mess and you have to be very careful to make sure you see who did not get crossed out. In this case, the survivors on the top are 4 times 7 times 6 times 5 times 4. Now, you would probably want to get out a calculator to work this out, just because it's a long enough problem. And this isn't an arithmetic class, but it ends up being 3,360. I invite you to try the part B. Pause the video and give it a try. And you're always welcome to pause the video and give it a try. But let's see what this one is. Well, 11 factorial's got a long way to go. 11, 10, 9, 8, 7, 6, 5, 4. Am I going to make it? He's not going to make it. That was an Animal Kingdom illusion for anybody who's ever ridden dinosaur. On the bottom, I got a bunch of factorials. Well, the first one is just a 1 factorial, so it's over as soon as it begins. But the 4 factorial is 4 times 3 times 2 times 1. I'm trying to keep my digits lined up. The other factorial is also 4 times 3 times 2 times 1. And at the end, I've got a 2 factorial, which is 2 times 1. Go for the jugular. Go for the biggest factorial you can, which in this case is 4 factorial. There's 2 of them on the bottom. I'll just choose that one to eliminate. And everything else I can do piecewise. Now, another trick to canceling is to find 2 numbers at the bottom that multiply to match something at the top. For example, 4 times 2 is 8. There is a factor of 8. So together, the 4 and the 2 will take out the 8. And the 3 and the 2 multiply gives 6. So together, the 3 and the 2 take out the 6. And what does this leave on the top? Because notice everything left on the bottom is now just a 1. If you can't see it, I'll highlight it. There's a 1 there going across. There's a 1 here. And there's a 1 sitting right there. So now that there's only 1s in the denominator, I don't have to worry about this fraction anymore. Who survived on the top? The 11, the 10, the 9, the 7, the 5, and I believe that's it. 11 times 10 times 9 times 7 times 5. I'm going to attempt to do this in my head, but I'm going to call it out as I do it. 7 times 5 is 35. 35 times 9 is the same as 350 minus 35, so that's 315. 315 times 11 is 3465. And then the number at the end is 0 times 10. I hope I did that right. 11 times 10, I was just trying to show off, times 9 times 7 times 5 is 34,600. Yeah, 50. All right, so the point I was trying to make, besides trying to do some fancy arithmetic in my head, is that when you have expressions involving factorials, usually ratios, some factorials on top of some more factorials, you can brute force it by trying to calculate each factorial individually. But there are some factorials, such as this one here that I'm about to highlight in green, which you probably won't be able to do that way because the numbers get ridiculously large. So it's important and sometimes mandatory that you understand what the factorial means by writing out its multiplication problem. And when you have one multiplication problem on top of another, expect a lot of canceling and then gather up the pieces and see what you're left with.